Is it visible, Dr. Subbu?
Yes, sir, it is visible.
Fine. So good morning, one and all. The first talk of the inning is Introduction to Additive Manufacturing. Myself, Dr. C.P. Paul from RRCAT. I'll be talking on two major aspects. One will be talking the importance of additive manufacturing. Why do we need it? What is the basic philosophy? And after that, probably we'll jump into some of the work that we did so that it will be a showcase for you guys and you can think of how the things can be taken to new level without going into the fundamentals of that. I'll be showing the parts and these things so that you can understand and try to grasp the things and knowledge during the FDP next 5 days so that you can also try to make something of that order. Let me introduce about what is RRCAT. Most of you must be knowing, but for the completion, RRCAT is a premier R&D institute under Department of Atomic Energy, Government of India, engaged in non-nuclear frontline research areas of lasers, particle accelerator, and related technology. When I talk of the related technology means anything which is required for the lasers development or particle accelerator development, we are doing that job. Let it be making a RF power supplies, let it be achieving ultra high vacuum, let it be making advanced magnets. So we have people working in this area and contributing to that. We are also the Constituent Institute of Homi Bhabha National University, a deemed to be university under Department of Atomic Energy. We are about 1570 employees with 45 PhD students. These are the external PhD students and almost same number is for the department people. We offer MTech projects to 142 plus students every year. These MTech projects, like the students working in different national labs or different institute in the country, and they want to pursue their project work here. So they can write to us, they can, and then after that, some of us will be very happy to guide. You can join RRCAT through BRC training school, or if you are a PhD and working in a niche area and have a vision to contribute in a big way, then you can join us with the K.S. Krishna Research Associate. In this, you can work 2 years as an associate, and after that, you can be absorbed in the department. You can pursue PhD from RRCAT in the area of engineering physics, life sciences, and engineering sciences, specifically in mechanical engineering. We also offer orientation courses on accelerators, lasers, and related technologies, OCAL, every year to 40 plus students. And the idea here is to give opportunity to master students in their final year for 8 weeks so that they can come and work with us and understand how research is done. And if they are good with that, they can think of taking research as a career. Coming back to our lab, Lab is basically working at the junction of advanced design methods, material science, manufacturing, and material processing. And we are from system design development to material processing to material testing to qualification validation to multi-physics modeling. And our idea is to produce groundbreaking high impact results, create an innovative LAMP technology, and make a good ecosystem where our research endeavors and collaborations are clearly visible in the global scenario. This is a team. I have 4 students working directly and 15 people focusing on the development and the processing of the different applications in the lab. This is the book that Dr. Subbu referred. Recently it is issued and it is available now, Amazon and Flipkart. When we were planning this work, we were thinking, yes, there is no book written by Indian authors and Indian styles covering the syllabus proposed by different IITs and different NITs. And most of the people were counting on foreign authors. So when we took this chapter, when we took this assignment, we had an emphasis it should be a economical viable solution for the student, should be affordable. Then therefore we went to the McGraw-Hills and now brought the price to 700 rupees for the book so that each and every student can buy and use it for their thing. And it encompasses most of the examples from India so that you can understand and appreciate how additive manufacturing is being taking place in India. So let me come to the core talk. If you talk of the Industrial Revolution, you see First industrial revolution started at the end of 18th century when steam engine was invented. And second industrial revolution came into figure when we had electric energy invented and people started making, who changed the whole scenario, the way it was being done, after first revolution. Then in the third industrial revolution, we had semiconductors, discovered. And after that, a big revolution came in electronics, telephones, PLCs, NC machines, and everything has changed. Managerial point of view, there would be lean manufacturing coming in. So brought a, big change in the whole scenario. We are on the verge of fourth industrial revolution, and which is basically driven by internet and internet allied technologies. And it's basically a physical, cyber physical system. It is a cyber physical system. And what is happening when you are going from industry first revolution to fourth industrial revolution, you see the productivity and complexity is increasing, and we have to be more, versatile in thought process, more elaborative to contribute. And the difference between different disciplines, if you talk of electrical, mechanical, electronics, this is slimming every day. And even if you are expert in materials and manufacturing on some specific title, you cannot contribute unless you have a big picture of other field. So that is the demand of the time, and we all have to gear up for this. Now, when we talk of Industry 4.0, I already told to you guys that this is basically fueled by the internet and IoTs. We are talking of digital mapping and visualization of the real world, and we are more focusing on interconnectivity, automation, machine learning, and real-time data. So this is the whole world and how the things are done. When we are talking of this, we are talking of connected world, we are talking of smart factories, we are talking of smart products, and we are talking of a fusion of a whole cycle. It's not earlier what was happening when we are talking of manufacturing and business. It was seen in silos. They were working in silos. But today we have to take a holistic view, not only in the production, design, other things, but also you have to come up with a bright solution so that you can contribute in a bigger way to the Industry 4.0. If I tell you the reference architecture model for the Industry 4.0, it has got two types. One is type instant, two elements. One is type and instance. Type when it is in conceptual and product level, instance when it becomes realized. There are sets which is at a level A here. Then and the sets can be physical or non-physical, like software and ideas. We have to integrate all these things to get the information, communicate all the information to desired formats and predefined protocols. And after that, processing the available information to convert into useful data, removing unwanted information, and make it a formal description of the function so that it can be used by ERPs. And after that, we should be able to contribute to decision making in the business. So this is the basically a model that people are talking of. And when I talk of this Industry 4.0, probably we must be thinking, when I'm talking of so much of these things, where is additive manufacturing into this? Additive manufacturing is here. You see, Industry 4.0 is basically counting on 9 pillars. These are IIoT, cybersecurity, additive manufacturing, augmented reality, big data analytics, autonomous robot, simulation, horizontal and vertical system integration. When I talk of horizontal and vertical system integration, it means we have a very good communication among the different sets. Today, if you see any industrial setup, there is a very good flow of information in a vertical form. And when I talk of the vertical, when I talk of horizontal communication, it means you have a Tata's group, means you take the case of Tata Group. You have many entities like Tata Motors, Tata Consulting Engineers, Tata Service, TCS, so many things are there. And is there flow of information in different SBUs of Tatas? And if it is there, then that is the horizontal communication and horizontal integration. So that is the thing we are doing, and we have to come up with, and we have to consider this part that additive manufacturing is going to support and make the things in a big way. Now, when we understood the importance of the technology, probably we have to see how was thing done in the past and what is new this thing is bringing in. Earlier, we know that most of the things were made by deformation, casting, joining, and whole the manufacturing technology was predominated by subtractive operation. Now the time has come when things are changing fast, specifically in 1987, when the minus sign converted into the plus, and subtractive machines, which were CNC machines like this in the floor, became a white collar job machine as an additive manufacturing machine. And this brought big change in the manufacturing and other things and whole change the scenario. Now, if you talk of what is made by the this technology, I'll go to the basic definition of the process. As per ESTM 52900, this is a process of joining materials to make parts from 3D model data, usually layer by layer, as opposed to subtractive manufacturing and formative manufacturing methodology. So this is a definition given by ISO and ASTM 52900. Now, if you see this and I try to understand the definition, you will find out that it has got 5 things into this definition. One is, it is a process of joining of materials. It starts from 3D model data. Typically, it is a layer by layer built up approach, and the process cannot be classified as subtractive manufacturing and formative manufacturing. If we put these 5 criteria in our mind and try to further focus on different process, you see there is a large number of process. And if you want to know whether these processes are qualifying for additive manufacturing or not, please prepare this table and see whether it is qualifying or not. And if you see anywhere in the process diagram, it means the process is not good for to be classified as additive manufacturing. For example, if I talk of hydroforming, hydroforming is not a process of joining of material. It doesn't start with the 3D model data. It is not layer by layer built up approach. And definitely it cannot be classified as such. Therefore, it is only one Y is on and all are no. So this is the way how can we see and put the process and understand and define whether the process can be classified as additive manufacturing or not. I will tell you the first example when we talk of conventional welding. Conventional welding is really process of joining of materials, yes. But conventional material welding doesn't start with a 3D model. It is not a layer by layer build up approach, though it is not classified as a subtractive methodology and formative methodology. So what the people did is they extended the concept of additive manufacturing to the conventional welding, and they came with the process called WAM, wire arc additive manufacturing process. So then it became, additive manufacturing. So this is a effort, there's opportunity to modify the existing process. Can it be brought to this level and classified as AM? If we just focus on these 5 points, probably we will be able to do justice and bring the change into the system. Now, if we talk of the synonyms, so many names it's known, very commonly known as 3D printing. But 3D printing is like a layman's word, but a real standard word is additive manufacturing. And all these names I am showing you here, like additive fabrication, layer manufacturing, free-form fabrication, solid form fabrications, all these things started with the different labs. Every lab started giving the name as per their convenience. And finally, ASTM came and they said, no, boss, we should have one name. And that one name is additive manufacturing. If you see, this concept is not new. It existed since long. And I'll say it is a more nature's way of growth. See how a seed is converted into a plant. It takes the things all around, grows, and become a plant. How an infant becomes an adult. It eats, drinks, plays. But effectively, if you talk of the growth, it is additive. And we also tried to do something in the past by making a house. You see, we used to bring brick and mortar, and we want to have different shapes and geometries as per our requirement. I will not say that that was additive, but now today what we are seeing is additive because of the better control, better process, faster computations, and superior technology. Now, if you compare additive with subtractive and formative technologies, you'll find that we score very good and green technologies, because if we compare with these two guys, probably we are using less material. We do not have a limitation in terms of materials. Shapes, we are not bothered, we can think of. Yes, we are suffering at some locations like surface finish and dimensional accuracies, but I am confident with the time as the technology matures further, these things will also be taken care. The most important point of this comparative is what is buy to fly ratio. Buy to fly ratio means what is the material I buy and what goes out of my manufacturing, my unit. You'll find that it's very attractive. And when you talk of the number of parts, you'll find that in subtractive and formative, as the number of part increases, the cost per part goes down, but it doesn't happen in additive. So it is very good for the low volume manufacturing, and specifically when we talk of customized product, which is the trend of the day. Now, when we talk of all these things, and I say that additive is making big thing, very attractive process, making this, you must be thinking, why should you go for additive manufacturing? When we talk of going for the additive manufacturing, I will say what is industry perspective. The industry perspective is we are all seeing cutthroat competition. And I'm showing you here a picture of a car. Just to start making you thought over that we have, what is the car market today? You see, we have so many competitors in car market in India. You see, we have Suzuki, we have Honda, we have Hyundai, we have Kia, we have Mahindras, we have Tatas, so many players. And every player is coming with so many models in itself. They have hatchback, they have sedan, they have SUV, they have compact SUV, so many cars they have. Though the car market has increased in size in last 20-25 years, but you'll see that the average car sold per model has gone down. And when we talk of average cars sold per model has gone down, it means it is difficult to control the cost. Why is so? Because when you talk of the cost of a car, I'm not talking of the commercial aspect, I'm talking of total manufacturing aspect of it. It will have two costs involved into it. One is the development cost, another is the manufacturing cost. And when the average cost of the car, average sale of the car per model has gone down, it means the development cost has gone up, because finally development has to be incurred from there. So this cutthroat competition is making us to think over, should we pursue in a conventional way or should we go for a different methodology so that the development cost can be brought down. We all studied during our UGs that Carnot efficiency is the best efficiency that a system can have. And we also know that it depends on, efficiency is 1 minus T1 upon T2, where T2 is the source temperature and T1 is the sink temperature. And if you see the conventional way, we cannot increase the temperature of the sink. So you have to increase the temperature of source. It means you have to operate your machine at the higher temperature, and that is the only viable solution. And when I say that when you are increasing the operating temperature of the system, means I am challenged to go for efficient design for the appropriate heat transfer. We are challenged to have a material that can process and that can withstand that high temperature. And it's a big thing when we are working with the limited scores, so resources, and the requirement is increasing. And further to these 2 points, another thing which is coming into the scenario is the fast changing technology. We see there is a 65% success rate for the new products with the superior technologies coming into the market. Some of the very conventional example of these fast changing technologies, very small concept that, that kills the market nowadays. For example, if you talk of the car rentals or taxis, the idea of Uber and Ola killed. If you talk of, delivery food market, you'll see the Zomato, Swiggy, the way they came up and made the things, everything is killed and brought in a different scenario. The availability of thinking, you see the banks, how the internet is adopted, how applications is adopted, and normally people do not go to the bank for any of the transactions, where there used to be a big queue in the bank every day. So this is the fast changing technology, and industries have to adopt and fastly, move ahead and become the experts, unless they are not going to survive into this market. Now I'll be telling you another part of the coin, other phase of the coin, which is the customer aspect. Now customer, they have more number of variants they have now. And if you talk of the product lifetime is decreasing. When I say the product lifetime, it means the duration for which the particular product can be sold without modification. You see car market, every 2 years you have a new model jump in, and people have to go facelift, face change, or something like that they have to do so that they can survive into the market. Therefore, I'm saying the product lifetime is going down. And if you talk of the complexities, it is increasing invariably. We have so many features you want in that. Many features means more complexities. If you see the car engine and you just open the bonnet of that, some 20 years back old car and now car, you'll see how the bonnet has changed in last 20 years, how the configuration of the engine has changed. People are talking of smart processing even in the while car operation. This is making a big thing. And there is also a big change into the customer perspective in terms of the delivery. Now, if you come with a very big and great idea and you say, hey, I am come in the market with this very nice product for the customer, the answer will be from the customer side. Thank you very much for the product, but I wanted it yesterday. So this is the customer thing. We are crushed from the industrial side, we are crushed from the competitor side, we are crushed from the customer side. Now issue is what to and what is the way out. The way out is probably immediate delivery of best quality products with all possible features and at the lowest possible price. So this made the things different and changed and make the things happening in big and better way. Easy to say, difficult to do. Now let's try to understand and see how this thing can be achieved with additive manufacturing. How can we contribute in a product life cycle or in development of a product using additive manufacturing? This is a conventional manufacturing method. You see, we start with the synthesis, analysis, documentation, and drawing in the design step. If we go for production, raw material procurement, tool procurement, CNC in the production part, then we go for a quality check, we go for a packing and usage. This is a typical conventional manufacturing cycle that we adopt. Now, if you put additive manufacturing into this, you'll find that there are many steps going out of the way. When I talk of the going out of the way, we are applying a time compression method and technologies so that the product cycle, development cycle goes down. And when I say the product development cycle goes down, it means the development cost goes down. See, how are we achieving this? In this additive manufacturing, we are making 3D model. We are not going for any documentation and drawing. Means there is a saving. We have a software who are doing the process planning. We are not doing anything by ourselves in additive manufacturing. While in conventional manufacturing, you might be sitting and then thinking of whether this job has to go to machine shop or it has to go to, lathe, or it has to go to fabrication shop or do some other processing. So that is not there. We are changing that part. After that, if you talk of raw material procurement, the day we start thinking about the product, we can start the procurement of the material. Because in this additive manufacturing, most of the product that we are using, they are shapeless material. They are not into some defined shape. The problem we face in conventional manufacturing is We cannot start the procurement unless the design is finalized. In our case, for example, you start off, is bringing a block of say 100 millimeter by 100 millimeter by 100 millimeter for particular application. And suppose design happens to be 100.5, we cannot use that. We have to make compromise. But in additive manufacturing, so far as it is within the built-up envelope of the machine, we are okay with. And we can state the procurement immediately. And this makes the thing into big and better way. We can talk to the suppliers. We can ensure that we can talk of economic order quantity from them. We say we want 10 kg or 100 kg or 500 kg. How much discount are you going to offer? Which is not possible conventionally. There is no need to have special tool procurements, as everything is inbuilt in additive manufacturing. So these 4 steps are making a big change in the whole technology and making the things further different and different scenario. If you talk of Indian government's emphasis, we are having a smart manufacturing. You see, the Niti Aayog has identified 15 disruptive technologies, and smart manufacturing is one among them. So country is ready, government is ready, and it's time for people to be ready to take up the assignments. Now let me tell how the things are coming as over methodology. It will have 3 phases. One is pre-processing part, processing part, and post-processing part. In pre-processing part, we need to think about concept generations and design, where we use CAD, 3D scanning, CAE, and numerical analysis data to build the shape. We think of customization of design by giving appropriate file conversion to the machine-specific format. We think of orientations of the product. We also think of arrangement of the parts in the build plate so that we can have a very good, faster processing. When I talk of arrangement of parts in build on the build plate, means I'm talking of the nesting of a product into the build plate so that we can optimize and use the space and better possible with less production time. And the third step of the pre-processing is going to the machine setup. Think of layer thickness, think of rastering patterns, think of support structure generations. So this is at the pre-processing stage. After that, we take this file to AM stations. We do the layer by layer processing, and there is a closed loop control if possible. And once this is done, the product comes out and it is sent to the post-processing part. In post-processing, we can use either as it is, or if surface finish requirement is there, which can be sent for the machining or any other finishing operations. If there is a need to change the property, bulk property of that, probably we may have to go post-heat treatment. We have to go for removal of support structures. And finally, we may think of doing some painting or coating for having a better aesthetics. After this, the final product comes. And this is a typical methodology of AM, what is happening today. So much when we talked about, let's focus on the advantage, limitation, and sustainability of the additive manufacturing process. Advantages, first is complexity for free. This is the buzzword. See what is happening when you talk of making a product using additive manufacturing method. The biggest advantage we have when we convert our 3D model into 2D slices, the shape becomes very simple and easy, and it brought complexity for free. In conventional method, as you go on increasing the complexity, the cost will go up and up like that. But in additive, it is not so. When we talk of the second advantage of additive manufacturing is a simplification of part fixturing, because here we are using non-contact method for the processing. In conventional method, we have to think of cutting forces when the product is made. We have to think of the high temperature that may having the bulk high temperature. So these things has to be considered while defining the part fixturing, which is not the case here, and it makes it simplified. The third part is the mass customization. Means you can think of changing anything anywhere in the part without much compromise without taking much time. So this is the third advantage of additive manufacturing. Another beautiful example is, which is fueling the industry 4.0, is the integrated components. Can we have some sensor embedded part into this so that it brings to new level and new height, make the things happening in a bigger and broader way? It is the advantage. We can use different materials at different locations. We have a material design freedom, and we can focus on feature-based design and manufacturing using additive manufacturing technology. Means when you want a wear-resistant surface, you go for a material which is wear-resistant. And if you want a thermal conductive bulk, you go for a material which is more thermal conductive. And if you want to have more transfer this, it is easy and better to work on this and plan the things in bigger way. When we talk in less level, we have a logistic freedom. When we talk of the logistic freedom, means the things are interconnected. You can send your design to different part of the world, take the feedback and come back for the manufacturing. That sort of advantage we have. The seventh is reduce wastage. When I talk of the reduced wastage, it means we can nest the part. Nesting is done appropriately so that maximum volume utilization is taken place. You see the example in the picture that I'm showing you, how the things are done here, and that is the advantage of AM we can bring into the game. When I talk of the advantage, I should also talk of the limitation of additive manufacturing technology. Today, the cost of production is very high. But I'm confident with the popularity, with the more players in, with the innovation in this area, the production cost will go down. We talk of the mechanical properties. Still, it is a under consideration. People think of how will it behave, what will the performance. This is a doubt. But I am confident this thing will also be improving with the time. Today, we have issues of tolerances and surface finish. To a great extent, we could solve, but still, it can be brought to next level without any problem, and things can be resolved. Today, we have a limitation of limited build volume. The volume of the machine governs it. With the innovation in this area, this will also be resolved. And the fifth limitation, it has got a stair-stepping head because of the inherent processing, where you have layer by layer. This shape becomes like this because of stair-stepping effect. This can be resolved with the time and make the things happening in a bigger way. Let me focus on the classification additive manufacturing. I'll not go to the big deep of the details of it, but just touch upon so that you understand how ASTM classify the process into this. As per ASTM, the process is classified into 7 processes: part polymerization, powder bed fusion, material extrusion, material jetting, binder jetting, directed energy depositions, sheet laminations. And here you have a different vendors who are supplying different sort of machine, and this is the commercial name of the machine that people are using. Part polymerizations, and thus people normally use 2 approaches: top-down system approach, in which you have a laser systems scanning from the top, and bottom up is bottom. Simple. You have a liquid photopolymer selectively cured using light activated polymerization. That is the crux of the process. I won't be going to the detail of it. Probably some other speakers will take up. The application areas are patient-specific models, functional parts, implantable device, tissue engineering, microfluidics. This is a great place to work on, and people are using in this area. Another technology is material jetting, and thus there are 2 basic technologies. One is continuous jetting, drop on demand. What happens into this? The material is placed here, the material is drop by drop, and the shape is built. And both the technologies are equally competent and competitive into the industries, and people are working on it. The various variant of this technology is aerosol jet technologies, laser-induced forward transfer, ballistic particle manufacturing. And these are highly used for prototype development, patient models, and medical wearables, jewelries, and electronics. And really very much useful into different and contribute in a big way. The third is material extrusion, which is most commonly used machine like FDM, fused deposition modeling. And in this, material is melted and brought and deposited the way they want. This is also very good for the concept modelings and functional testing. It is widely used for aerospace applications, specifically unmanned aerial vehicles. Convention is not possible to build it. This is the biggest advantage of additive and taking a big lead in this area. It is also being deployed for pre-surgery planning and rehearsal with the model and jigs and fixtures for the test and trial. So this is the thing where material jetting is being used. Another technology is binder jetting. In binder jetting, what people do is they spread simply the material to be joined, and after that they just drop a liquid bonding agent so that on the powder bed, so that it is just get deposited and shape is built. This technology is also very attractive and very commercially available into this. You can make colored prototypes, decorative arts, metallic components, toolings, and electronics used in this particular technology. Another technology is sheet lamination. In sheet laminations, we have a sheet, we cut with the lasers and keep on joining layer by layer. This technology is not doing so great, but still it had a very good applications in the microfluidic devices, toolings, prototype visualization in smart structures. And this has got very good attraction when it comes to making some, sensor embedded things into it. It is taking a lead. The fifth technology is powder bed fusion. And thus, in additive manufacturing process, thermal energy is directly fusing the region of the powder bed. We have a powder spread over here. The laser comes, melt, and then the build plate is taken up, the dispenser plate is taken up, spread it over, and that is the technology of the powder bed fusion. This is widely used in aerospace, tooling, medical, and automotive, and a big game changer. IITPKD, they have M290 machine from US, which is basically based on powder bed fusion machine system. The last technology is directed energy deposition. When we directly send the energy and melt the material and deposit, this particular process has fusion, focused thermal energy, fusion by complete melting, fusion during deposition. And it's a great use. In this particular technology, like you can have a 3 jet coming on from the center, laser beam is coming and melting and depositing. That sort of thing is possible. You can use other way around also. You can have a split of the beam into 3 parts and then allow the material to come from the center and deposit. So direct energy deposition is also of great use. It is very useful for near net shipping, making a large components, being widely used for the tooling, biomedical, cladding of high performance materials, and repair. So these are the 7 technologies that I talked and gave an overview about it. And quickly, I'll be telling you what are we doing at RRCAT as a laser additive manufacturing part. Being the laser institute, we are more focused on additive manufacturing using lasers. And if you see the classification of laser additive manufacturing LAM, it can be classified into 2 parts, powder bed fusion and directed energy deposition. And when you talk of the powder bed fusion, it can have 2 parts. One is laser sintering and laser melting. The difference is in laser sintering, we are only melting the surface of the metal powders or any powders, and we are making them coalescence. But in laser melting, we are melting full powder and depositing. That is the basic difference between these 2 methods. And in directed energy deposition, the feed material can be either powder or it can be wire based on this classification comes with the picture. You see both the machines that are operating into it in directed energy deposition, how the things are done and how the powder bed fusions is building the component. In DED, we have a functionally graded structures. We can be used for multi-material components. We can use large near net shape components. Complex geometries can be taken care of. But in powder bed fusion, the unlimited complexities, refined microstructure, lightweight structures, and thin features are the advantages. So both have got different domain to play work. When it comes to multi-materials, DD is the winner. When it comes to the complexities and making lightweight structures or very thin geometries, powder bed fusion is the winner. So both technologies can be applied where we want to use and based on this one. When I talk of the technologies of these things, probably very big question comes, what is the global scenario of this technology today? If you take a scale of technology readiness from 1 to 10, you will find that LAM, laser additive manufacturing, is somewhere 5 to 6 for aviation and automobile, 8 tooling space and drones and defense, and dental medical instrumentation and implants for at TRL 10. And this shows that people are really striking hard and taking the technology into bigger way. Now, when we talk of this, probably we have to come down and think of what is happening in Indian scenario. Most of the Indian industries are basically focused on plastic AM machines. We have metal additive manufacturing in leading academic institute in the country. People are joining the mission. When I talk of this, probably we have to think who is having these metal additive manufacturing machines in the country. We have RRCAT, we have CMTI, ERCA Hyderabad, DMR Hyderabad, GITRE, IIT Kharagpur, IIT Bombay, IIT Kanpur, IIT Palakkad, CISRI, CGCRI, IGTR, CTTC are the government player, public funded institutes. We also have now metal additive manufacturing with the private players like Wipro, Honeywell, 3D Incredible, Dentcare, GE, Objectify. Things are changing. And not only people are buying the standard machines, but they are also now involved in the development of these machines. Like you have RRCAT, CMTI, CMARE, IIT Bombay, IIT Kharagpur, PSG College, Intech. Now we have MS now, we have BFW now. The list is ever increasing in Indian scenario. And what I'm saying, when we talk of increasing scenario, there is a lot of effort and opportunity for us to go ahead and contribute to the area of the technologies. With this Indian and global scenario, I'll come to what we have done. We built this machine, powder bed fusion machine, indigenously based on the 500-watt fiber lasers with powder spreading unit, our own GUI, a galvanized scanner and controller. You see how the thing happens, the spreading of the powder on the bed. And after that, we have a laser beam coming, melting, and giving the shape of this. Once this is done, the powder goes down, another layer is put, and this just go on continuously till the whole component is built. The volume it is having 250 by 250 by 250. Beam diameter is 500 watt. It can further be brought down. This configuration presently is 500 watt. Layer thickness we can take from 25 to 250 micron. And big things can be done and tried out in bigger way. Another beautiful work that we did is development of indigenously laser and TD machine. This is basically based on a 2 kilowatt fiber laser. It comes here, we have a machine putting and depositing layer by layer, given the shape. We have dual powder feeder. You can change to powder, feed them, change the powder during the fly. That's what the advantage this machine has. Again, it is built in indigenously. Same volume, 250 by 250. We have 5-axis controller from Siemens 810D, and it can use either fire or powder and make the things happening. Purity in the glow box can be better than 20 ppm of oxygen or better than 30 ppm of moisture. This is. Now, when I talk building of the indigenous technology, I'll also tell here, if you buy this machine from the commercial market, it will be costing somewhere around 3.5 to maybe 5.5 crores. And when we built this machine in the country, it is just 1 crore or so. So that is required for things to happen in the country to take the things leap to the another level. Similarly, if we talk of DD machine, the commercial machine will be costing somewhere 5 to 7 crores. And when you do this in the country, we did it with investment around 2.5 crores. And that is the change and big change into the whole scenario. We're increasing the volume, going for the larger components, larger shapes. Now we can have a large volume like 1.6 meter diameter and 1.4 meter length. The component can be built on this size. We are collaborating with many institutes. Let it be BRC, IGCAR, let it be BRC, IGCAR, IPR, ARCI, many institutes we are collaborating. Just a minute, I have some urgent call. Just a minute. Sorry for 2 minutes, I'll stop. Sorry for a small. So we are working with Vikram Sarabhai Space Center, Trivandrum. We are also working with IIT Indore and many other IITs. IIT Palakkad also, we work together with them. You see the logo here. So the idea is to support and promote the technology in the country so that we can take it to next level of the operation. Some of the example when I talk of the one of the beautiful example is making Deloro 50 bushes. These bushes earlier were made using conventional method. And why Deloro 50? Because Deloro 50 is one of the material which is used in reactor to circumvent the galling problem. So what the people were doing is they were used to take machine SS rod, and they used to deposit columni or Deloro 50 material or wire using conventional method. And as a result, what used to happen that there was a lot of dilution of the substrate, and the people has to go for a lot of machining to give the shape of the bushes. As a result, what was happening is they used to take 45 days to make such bushes. And after that, we went for conventional manufacturing. We went for the additive manufacturing. We gave a helical upward motion up. And once we done this deposition, we did the small machining, and it helped and make the things happening. And the forward, which is being done in 45 days, could be completed in 72 hours. So this is a big change that additive manufacturing brought into the domain. Another beautiful example, we took it for our program in building the mesh type spaces for fuel cluster simulators for PHWR, pressurized heavy water reactors, 540 megawatt electric. This particular component you are seeing in the BRC, they were trying to develop this for the simulators. It has got very nice, see diamond structure here, some triangular structure and circle. The wall thickness is around 0.5 millimeter, and dimension accuracy, they are asking about 100 micron. And this will be used as a spacer in this to keep these heating tubes separated during the assembly and in the assembly. They used to do this job with the IDM wire cut, and it used to take 7 working days to build one component. When we took it to our powder bed fusion machine and built the same shape, to the surprise, the fabrication time comes down to 2.5 hours. So you see, 7 days converting into 2.5 days. And this is the change where additive manufacturing is bringing. Another beautiful example is making honeycomb geometry orifices for our IG car friends. They try to build this honeycomb shaped orifices, and these are used in pressurized fast breed reactors as a pressure drop devices, facilitating uniform temperature distribution and flow of liquid sodium. Conventionally, these are made, people tried using GTW, conventional casting, investment casting, but they had very limited success. When we started and deployed LAM, things changed and we are successful. Another beautiful example is making the compact heat exchangers, where you have a compactness, low pressure drop, high effectiveness, everything is built. And we are able to make a small orifices throughout, small channels throughout the heat exchanger, and the size is 2 millimeter by 1.5 millimeter rectangular shaped. This is possible in this, which is not possible to have subshape conventionally. And these has got potential application in supercritical CO2 Breton cycle based systems, which are likely to be used for solar thermal energy generations and generator for nuclear reactors. So I'm talking of, the very high end product, which is not possible conventionally to build. And it is showing the way and showing the hope where things can be brought and make the things to happen in bigger and broader way. Another beautiful example of deploying the additive manufacturing process to deposit high performance material. We all know that in Japan, when Fukushima accident happened, after that, there is a lot of thrust to have more and better safe reactors. And what people are asking us to deposit a 0.2 millimeter thick silicon clad layer on this tube of zircaloy. And this zircaloy tube is 10 millimeter diameter, 0.6 millimeter thick. You see a 0.6 millimeter, we are depositing 0.2 millimeter over that. We developed, we operate, and we optimize the uniformly silicon carbide deposit, and these things are now being under examination at DRC. So I'm saying these advanced components, when you talk of different material, making a component which is altogether not thought of in the past is possible using additive manufacturing technology. When you talk of copper, we did some experiment. We tried to identify the gaps and try to work on, and very good deposition got. We collaborate with NIT Warangal to build some component, some SS tungsten carbide composites. Big change we got, and we deposited. And you see how the hardness increased with the inclusion of tungsten carbide. It's a beautiful example when you can have a different material built using additive manufacturing technology. Another beautiful example is this is for ITER project. ITER is International Thermonuclear Reactor, experimental reactor, which is built in France. In India, IPR is the key and they are mounted. And this is the small plate that you are seeing is a part of a plasma driver plate. Here the requirement is they want to have a molybdenum on the top to resolve the erosion part of it, and they have a copper on the base. And what we did is deposition of moly on copper is not possible directly. They used PVD, CVD, some other techniques in which their thickness was limited to 50 micron or 30 micron like that, but they wanted a thickness of 300 plus micron. We deposited, we did the machining, and we could not achieve directly. Then what we did is we introduced a nickel layer in between these two guys. And when we introduce, things change and everything happened in a big way. So what I want to say is it's not the direct solution sometimes, but it provides indirect route to provide a solution and make the thing happening in bigger and bigger way. We also did the deposition of Delora 50 and stainless steel and make the things in bigger and bigger way. Another beautiful example of deployment additive manufacturing processes, can we use or make a 3D porous structure with graded porosity in the space. See, we as a mechanical engineer, we had been taught that porosity is bad in the component. I do agree. But this, I will add it here. This is just because we are not having a taming strategy to control them. We are not able to understand the mechanism of the porosity. We are not able to apply it effectively. That is the limitation. If you understand the mechanism of the porous material, we try to bring into that level and make the things happening in a big and greater way. Probably we can bring solution to some new areas and new problems. Because when we make the porous structures using additive manufacturing, we understand where are we giving the porosity. We are sure about the reproducibility of the porous structures. And when we have reproducibility of the pores, we have control on them, we will be able to understand the mechanism and we will be able to deploy them in a big way. That is the technology difference they are going to bring and make the things happening in big way. You see a microcity image of this porous material, it's changing in the space. And change of the space is not possible conventionally. Here we are talking of and making the things happening in different and better way. Many components we built, We built honeycomb core, spacers, hip plant, impellers, many things we did. And this is just, I gave you a showcase, all these things, so that you can appreciate the concept, you can think of using into your work and making things happening in a bigger and better way. When I talk of these things, I will also touch upon what are the technology challenges we have as a last phase of my talk, so that we can have thing in and understand, and then we'll take up the all questions from the participants. Now, whenever we talk of LAM, we also think of what are the opportunities we have as a people working in this area. I always show this 9 grid, 9 phases. We have a opportunity to work in machine, software development, process development, material and feedstock development, design for LAM, modeling and simulations, characterization and testing, quality control and assurance, application development, and education and training. So we have these 9 domains on which we have to work to make this happening. When I talk of the software and machine development, we know that it is now today required a huge capital investment, and we have limited resources. Can we have some innovation in this area so that cost comes down? Can we have some change in the design of the machine so that really it becomes, very user friendly, and our limited resources able to assure it, use it? That is the opportunity we have today to work on. And when you talk of the process development and control, we always say that it's being widely done, this. But issue is, can we extend it to next level of applications? Can we make it better reproducible? So that is the challenge we have, opportunity we have in terms of the process development and control. When I talk of developing a material feedstock and making it, today what are we doing? What are the material we are getting? Very few materials are available which are AM specific. We are using the material from other sources and trying to use it. Are they optimized enough? Because they built for some other process. Do we need to have a fine tweaking of the composition so that a better property can be achieved? Do we need to bring new alloys into this so that a better property can be achieved? So there is a scope for us to work on these areas. When today I talk of the laser additive manufacturing, it's more of the art. We understand it, we deploy it, and make it happen. But how this art can be converted into science and technology, so that with specific rules, so that everybody in this, and it's not person specific. So that sort of thing is required. Today, what are we doing is, we are most of the times using this technology as a replacement of conventional technology. See, I showed you many shapes in my presentations where we have replaced the component using additive manufacturing. Now we are going to the next level, talking to designer there, and we are trying to penetrate into it. Can we have a better design using this methodology where we unlearn the conventional manufacturing limitations and adopt in our design so that a better and good design can be built and made on? We need to have a very good modeling and simulation tools so that we can analyze. We all understand that analytic methods are not suitable for making complex structures. Numerical solution takes forever to make any components. Can we bring some nomograms, machine learning, some other algorithm into this so that we can simulate and model things faster and provide a very good review to the things? Another example and areas to work on is, can we have better characterization testing facilities? More sophisticated tools are required, like micro-CT machines cost few crores. Every lab cannot afford it. Can we have some other method so that these can be done? Can we have simulated low testing setup which are specifically made so that things can be brought and make the things happening in different way? There is a need to have a design codes, customer validation, certifying agencies, guidelines, so that this AM process becomes a industry viable solution. See, today when we talk of designing a pressure vessel or deployment of material for nuclear applications, we talk of SME section 8, section 3. When you talk of the welding, we say section 9. Can we have a very nice standard built on which everybody can count and rely? That is the area where we need to work, and which will provide a quality assurance and quality control, and specifically helping to bring many certifying agencies into this. And that is the challenge. And people are working on this direction, but again, we have a scope to work on. Can we develop some other novel applications, entering into new domain, showing our capabilities, working on dissimilar processing? That is the area to work on. And all these 8 areas are really good. But the most important is we need to focus on education and training, learning all these objectives so that curriculum development can be done, faculty development program can be run, and we brought this to next level of expertise, and this will make the things happening big and greater way. I will touch upon some of the advanced topic before I conclude. When we talk of this in my keynote address, I talk about the digital twins. When I talk of the digital twins, we have to understand what we are talking and how the things can be done. What is the concept? Basically, this is a merger of physical and digital world together. And when you talk of this, 2 objects are digitally and physically paired in such a way they can be descriptive, interrogative, analytic, diagnostics, predictive, and anticipatory. And what are we doing is we have a physical world, the way the physical world behave, the same thing we see in our digital world. And they are pairing, they are clone. It's a digital clone of the physical world, and that makes the thing different. And that is the concept that we are talking of, making it happening in a bigger and bigger way. For example, this is a GE digital wind farm, and they made it now digital twins. And this is a digital twins, and this is the real one. Now, if suppose thunder comes, storm comes, and after that, this fellow goes run very fast and breaks at some point of time, we do not know at how and what condition it failed. But if you have a digital twin, all the data and information is recorded. Similarly, if you make an aircraft is flying New York City to say Kochi. During the flight, if you want to know what is happening in the aircraft, what is the condition of the engines there, what is the situation inside the car, these things can be achieved, defined in digital twins. And that is the technology where additive is going to make the difference while making the components. We can have some embedded sensors who are transmitting the information without any problem to the sources and servers, and things are happening. Similarly, in marine world, can we have a submarine digital real one? We can think of where are the icebergs are there, accordingly things can be planned, and this, and that is possible to do it today. In power plants, we can have 2. One is the physical plant and the digital, where we are knowing what is the condition, what is the temperature, all these things can be seen and things. The concept is further access to the hospitals. You see, you have a real patient, you have a digital patient here. And what is happening, the patient is observed by some command center centrally located at some other locations, where you have experts sitting together and thinking about the patient, monitoring it, and then they set making the decision. And this can be anywhere in the world, need not to be your town. So this is making the change, and digital twins is making. Now, when I talk of these, how these sensors and things can be done and make the things. Today, when we talk of the industries, we talk of the production line. It's going to be changed into integrated manufacturing like this. Tomorrow, things are going and making the things different with the smart factories. Now, people have to work and study the concept of these things to have a full advantage, make the things happening, understanding, and making it different. When I talk of this, adopting the new technology, probably we need to focus on the challenges we have. It's not only the technical challenges, because when you talk of technical challenges, I can say we have to think of model composability. We have to talk magnitude and complexities. We need to talk of digitizing the legacy of whole thing and making things happening. This may be technical challenges. We need to think of how the workforce can be managed to this. Today, we do not have a lot of experts available to work in this area. How digital legacy is safe. What is the demand of the talent? How this can be embedded in existing structures, organization structures, to make the digital thread within them. So these are the workforce challenges we have. If we talk of the business challenges, how this should be sold, I'll not touch upon much. Then social challenge is one of the important point of this when you are making the twins fine. But again, how the human will behave, because again, we have to, there is a very thin line between privacy and sharing the information. And how will you take up? How are the people ready to do that? These are the social challenges we have. Today, when we talk of the hospitals, today we have our own people around. Even if we do not have the best of the facilities available, our morals are high. And that makes the things happening big and greater way. And that is a challenge, how we can adopt Industry 4.0 through additive manufacturing in these areas. When I talk of these things, you see how scenario is changing in terms of capabilities and talent search. Complex problem solving, critical thinking is now going up and up, while it was not that critical at the time. Now things are changing and making things happening in different way. What we have to understand is telephone took 75 years to reach to 1 million mark. Pokemon took 1 month. So that is the fast way of the technology things are happening, making things happening big and better way. With this, I'll stop here. To the summaries, additive manufacturing is novel methodology capable of providing new manufacturing solutions. There is a decent lead at international level. India is gearing up for the adaptation. RRCAT is the lead role from machine development to the process modeling. We are collaborating with national labs and academic institutes. Innovation is required, which is not limited to the process development and material characterization, but there is a need to tackle all 9 domains for successful development of technology. With this, I stop. Thank you very much. I'll take up the questions if there are.
Hello, sir. Thank you, sir. Thank you very much. It's a very wonderful talk. Even this is the first time I got an opportunity to attend your talk completely.
Thank you.
Your talk gave very insightful from basics to like current trends. Like whatever our title says, say additive manufacturing lab scale to field scale. This is a very greatest justification. More than that, I hope people can give a justification through the talk. Okay, so really thanks for that. Now this floor is open for questions. I request the audience may unmute yourself and post your question. If you are facing any difficulty, please write your question in the chat box. I will take up the questions. So there is one question in the chat box, sir, like in case of emergency situation, AM parts can be replaced or reproduced, same part can be produced with accuracy at a limited level.
It's a very good question, Punarasan. Yeah, sorry, I could not spell quickly. Yeah, no. So see, issue is here. It is true when we talk of the now Mars missions, or we talk of the especially marine missions. This is the solution. You cannot carry so many spares with you. Here, idea is, can we take some raw material and build as per requirement? And definitely today things are getting to that level. I will not say technology is matured enough to take up to that level in one go. Still some post-processings are required. But with the advent of the technologies, with the efforts across the globe, things will go, and we are confident that things will come and things will happen in that direction. And it's just a matter of time. See, the timeline about the additive manufacturing says by 2032, they want to make a full human body using tissue engineering, additive manufacturing based tissue engineering. So bioprinting they called. So that sort of thing is happening. Definitely in manufacturing also, when you make the replacement of part, so many things will change and make the things happening in bigger and great way.
Okay, sir. Thank you. Yeah, there is one more question from Rafiq Pare. He asked about which AM process is used for magnesium alloys.
For magnesium alloys, you can use both the methods. Powder bed fusion as DD method. There is no issue on that. But what we have to understand is what is the typical application according things have to start it. If you're going for a bioimplant applications and many other things, and what is the geometry requirements are there, based on that all these things are defined. But as far as the process is concerned, both are fine. And I'll just add it here. When we talk of directed energy deposition, we use bit larger size of the powder particle, typically 45 to 100 micron range for directed energy deposition. But in case of powder bed fusion, we go for a smaller particle size, maybe 5 micron to 20 micron, or maybe 30 micron particle size. So there the change in difference. So what I'm saying, both the processes are capable of making the components bioimplant. There is no issue on that. But only thing is, how do you want to this? And all these things have to be processed in a controlled atmosphere. And the purity of the system, purity of the controlled atmosphere, all these things are challenging when we talk of the bioimplants. So that is the thing we need to consider. But as far as the process is concerned, doable by both the process, and maybe some post-finishing applications may be required.
Okay, sir. Thank you. I think few more questions are there. How does laser powder interaction, especially reflective of material, affect the material usage in lamp application?
Pramod, this is a good question and really very fantastic. What you have to understand is how, if you try to visualize the, if you try to visualize the process, material interaction, how the material will interact with the laser. See, first thing we have to understand is the material here is in a powder format. And that is the advantage that when you have a surface, plane surface on which if a laser beam falls, it will be reflected directly. When I talk of the direct energy deposition, you have a powder cloud. And when laser goes into this, it sees the multiple internal reflections. And as a result, the absorption increases and catchment efficiency in a big way. Similarly, when I talk of the powder bed fusions, we have a powders which are not horizontal, but they are oriented, and all are having a circular shapes, and there are small spaces between those them because of their green density. The laser beam is falling on that and getting absorbed into a subsequent layer, and after that it's also seeing internal reflection, multiple reflections. So that is the advantage. Therefore, the efficiency is concerned. See, for example, you see in my presentation, I have already shown you the slide of deposition of copper. Copper is not a good material for laser processing, but in Archons we could do it. Yes, energy density has to be high, the speed has to be in different way, but again it's doable and it's done.
Okay, sir. Thank you.
Yes, sir. I have a quick question.
Yeah, please.
Yeah, I'm Ashwath from UK. So, is there any scope for friction stir welding of doing some welding issues to fix some welding issues in similar plate weldings? Because we work on aluminum composite for fuel tank applications. Is there any scope of additive manufacturing in welding issues fixing, sir?
Ashwath, the beauty of additive manufacturing is you can always think of having a graded layer. You can think of bringing two materials and make appropriate changes so that it becomes very nice and good for you and becomes very. For example, I gave you the example of deposition of molybdenum on copper. The moly and copper, they don't go well. We also made some titanium SS transition joints. The titanium SS don't go together. But what is happening when we make such joint, we have a freedom to bring a different alloy between these. It is like, you have three friends, 1 and 2 do not talk to each other. You can always introduce number 3rd, and 3 will, set these two guys in those. That sort of thing is possible. And if you use this technology and optimize the process appropriately, you will have the solution for the laser welding problem also.
Yes, thank you, sir. Thank you so much. And your presentation was so good.
Thank you.
Thank you, Ashwin. Yeah, so any other participants would like to interact with Dr. C.P. Pal? So please unmute yourself and pose your questions.
I think Dr. Ajit Kumar has asked whether the additive manufacturing will replace our all conventional manufacturing.
Oh, maybe I missed this.
No, this is not the, no, it will not, at least for next 2 decades, not. It will take time for that to happen to that level because it will not be very cost effective as far as today is concerned. See, a very big question the people think of, will EV replace conventional vehicles? Electric vehicle will replace. Yes, it will replace, but it will take some time. But today, as far as additive is concerned, still where you have a bulk material usage, you talk of making something which is in mass production. These things likely dominant. And what I am seeing is there would be change in the mindset of the customer. And when there is a change in the mindset of the customer and people are more focusing on making the components built for customize, then things will change and probably people will start thinking of shifting to 100% additive. But till that, as far as the economics is concerned, conventional will definitely going to dominate, and additive will not replace the conventional method. Because I will say these are these are, in spite competitive technologies, they are complementary technologies where you take the best of both the world and then start thinking on those aspects. That is the thing I will say will the better.
Okay, sir. There are a few more questions. This is a question from Madhi Murugan. He asked about whether different material are built in the same build.
In India, yeah, we see. I'll tell you, we have both the technologies, DED as well powder bed fusion. In DED, both the materials can be built together. There is no issue on that. Not only that, I'm talking of making functionally graded material. It means the first layer is having 10% of A or 90% of B, and second layer can have 20% of A and 80% of B. Like that, you can just keep on grading. So that is possible, and it's done. And a DED, it is very easy to do it. Powder bed there is challenge, but again, definitely there are some innovations coming in, and this will also resolve the problem in future to come.
Yeah, so there is one question from Naveen G. You mentioned about won't reactivity of the material affect the production, and also, like you said, lifespan of the product.
Yeah, this is again the point which is falling under the qualification as far as the lifespan is concerned. But again, therefore, I had been telling that we need to have a certifying agencies and things into the place so that we know real strength of it. But more or less, I will say here in most of the material, especially when you talk of the nickel alloys, the material has a tendency in as built condition to close towards the wrought material rather than a cast material. So we do not expect a lot of fall into the lifespan as far as the material is concerned. There would be definitely some residual stress into the material. That is one part. But again, accordingly, the system will be designed and done. And we also have an option to go for post-heat treatment and make the things better for us. So that is the answer to the second part of your question. First part is as reactivity is concerned, this is a challenge you have to really understand and try to learn from that key. How can you tame this problem? So therefore, when I talk of the making a system, we always say that the purity of the chamber in which the processing is done is better than 20 ppm or so, and you have to plan, and then only it is possible to go ahead with.
Okay, sir. Thank you. Yeah. So, Mr. J. Nitish Krishnan, he asked the question: can you tell about the additive manufacturing using ceramics and its related issues?
Yeah, it is a challenging task, especially when used laser. We attempted something. We are trying to make alumina titanium joint for some of our applications. That is one of the challenge, and it's really up to 1 to 2 millimeter. It's fine. After that, it cracks. That is thing. But how to tackle? We are working on. We are also trying to build YSZ, Yttria, stabilized zirconia on the stainless steel. So there is also challenges are there, cracks are there, porosities are formed. But again, no, we have to really find a sweet spot where things can be managed and done in better way. I will not say that it is not doable. It is very much doable. Only thing is we have to find out the window and plan and work accordingly.
Thank you, sir. So there's a question from Danish. So when can we expect the cost to come down?
Very simple. If you talk of the business models, the moment blue ocean becomes red, the cost falls. So again, I'll say, but I will not say just that way. We have to see in two perspectives. One is there is an inherent cost in the machines they have. People still working with the 50 and 60% plus margin. Big companies are working on those because they have sort of monopoly or so when the moment it starts breaking, things will come definitely down. Second part is people also have to think of innovative design in the machine itself, so that the input cost itself goes down. So that is the second level of innovation to bring the cost down. Therefore, even in I have emphasis, can we think of replacing galvano scanner or some other critical high cost items, so that the cost can be brought down. So we are working on those, and definitely this is the way we can do that.
Thank you, sir. So there is a question from Hagarga. Is it possible to use a plant fiber in AM process?
One of my PhD students is working in this area because we want to make a smart component. So what are we doing as we are implanting the optical fiber with the FBG fiber grating in the component itself. So we have a temperature information at the multiple location during the process, And when I'm talking about the making smart component, means we are extracting the temperature informations, putting some algorithm so that things can be controlled and cooling rate can be increased, or or heating cycle can be brought in spite of having a passive control on that. So that sort of things are done, and it's really possible to plant fibers. But again, it has to be followed with a strategy. So that is the important part, but it is doable.
Thank you, sir. If I understand that question clearly, like he mentioned about plant fiber, that means he's talking about natural fiber. Maybe that coming question is in line to that. Can it possible to use of natural fiber composites or biocomposites?
See, for example, when you talk of our metals, natural fibers and biocomposite fibers are not widely used. But again, for the plastic and polymers, wherever you are using this technology, they are very much doable. There are some studies about planting graphene into metals. A full research group is going on, so we can have a better properties. That is the part of the game, and people are working on this area.
Okay, thank you, sir. So Mohammed Rafiq is having one question which is not related to your presentation. So regarding his MTech completed students, have an opportunity to join RRCAT for internship or project position, like that.
Rafiq, I will say that we offer project to the final year students. So that is the open policy. There is no issue on that. But again, I would like to just share some of the things which is in the pipeline at RRCAT. First thing is I am opening our additive manufacturing to use services as a service bureau on the payment basis to the industries. And when we start doing this, definitely we'll have some revenue and we need some people to work on the projects. So these positions are always possible to go on. And when I talk of the project position, it will not be limited to the just learning an internship, but also contributing using design of additive manufacturing methods. So that is a plan which is likely to be realized in 1 year to 2 years time. Because finally is I have to this is the idea. Now I'm getting approval. First level is approval is done. I have to go to our governing board, get the things done. Once this is done, we are ready with that, and then we have to go to the people, ask for the job, getting all the businesses. And when this starts happening, definitely we'll have opportunities and project position at RRCAT to work on this area. Definitely, you guys can write to us, and that time we should be in better position to write it. And as far as the working for design for additive manufacturing is concerned in these projects, our emphasis is will be on the project basis hiring. You can discuss with us, and in spite of hiring a full-time, it can be project to project basis. That is the plan as of now, and if it works out, it will be well. And we'll be offering services in both the cases, in the additive manufacturing using DED as well as powder bed fusion. That is the plan in the near future. And after that, we'll be looking for some of the people to handhold the stuff, take the technology to the industries, whatever they developed at RRCAT, so that the cost of the technology further goes down, and we have people, and with the established market, easy for them to work on. So this is our plan in the near future.
Thank you, sir. I think no more questions from participants' side. Yeah. Sir, I would like to add one point with your presentation. Here most of the participants are like faculty members. So generally, faculty members used to say we are always having a funding crunch to do any research. Okay, because we have to buy equipment and then install and do the things.